Okay, everyone, we're back, and today we're diving into something that I think a lot of us have probably experienced, but maybe haven't thought too much about. That feeling when your computer just completely freezes up, like everything just locks up, and,
Mm.
you're sitting there like, okay, what do I do? And the only thing that seems to work is to, hold down the power button and do a full system restart.
Yeah, absolutely. That feeling of just hitting the panic button because it seems like one little thing somewhere deep inside decided to go haywire.
Exactly. It's like the digital equivalent of like pulling the fire alarm, when it's probably just a small issue. But
Yeah.
what if there was a way, and I think this is what we're going to be talking about today. What if there was a way to like target that one specific little thing that's causing the problem and just kind of nudge it back into place without having to like reset the entire system?
Yeah, that's a great analogy. And it's a really interesting topic because, as you know, our systems are getting more and more complex, and there's a lot going on under the hood.
Hmm.
And sometimes you don't want to have to resort to these, like you said, these sledgehammer approaches of rebooting the whole thing when it might just be a very localized issue.
Right. And thankfully, you sent me some really fascinating materials about this. We're talking about PCI Express, right? Or PCIe for short,
Yeah.
which is kind of like the central nervous system of a modern computer. It's how your graphics card talks to your processor and how your super fast NVMe drives connect everything up.
Exactly. PCIe is like the backbone, the high-speed communication highway inside your computer. And these materials you sent me, they all kind of point towards this really interesting mechanism within PCIe called function level reset, or sometimes you'll see it abbreviated as FLR.
Yeah.
And that's what we're going to be unpacking today, this idea that you can essentially reset a very specific component, a single function within a PCIe device
Hmm.
without having to disrupt the entire system.
Okay. So function level reset FLR. That's our topic for today. Now, before we get into the technical nitty-gritty, can you give us just a high-level overview of like what kind of sources we're looking at for this deep dive? Like where's this information coming from?
Sure. So you sent over a really good mix of stuff. You got some pretty in-depth technical documents, actual specifications from the PCI SIG, the group that develops the PCIe standard. So we're getting right to the source there. But then you've also got some forum discussions and blog posts from people who are actually using this stuff in the real world. So it's not just theory. We're getting those practical perspectives as well.
Oh, that's perfect because I think that's what makes these deep dives so interesting. It's not just reading from a textbook. It's like
Yeah.
we're getting into the minds of the engineers who designed it, but also the people who are actually out there using it and sometimes troubleshooting it.
Exactly. And from what I've seen in these sources, there's definitely a lot of interest in FLR, especially in certain areas like virtualization, where you're trying to isolate different operating systems and give them dedicated access to hardware, and then also in just general system stability. Like, how can we make our computers more resilient? So if one little thing goes wrong, we don't have to bring the whole house down.
Yeah, that makes a lot of sense. All right, so for everyone listening, our mission today is to really get a solid grasp on this FLR concept.
Hmm.
What it is, why it's important, where it's used, and how it actually works at a technical level. And of course, we'll make sure to connect all of this back to you, the listener, so you can see why this matters, whether you're a hardcore tech enthusiast or just someone who wants their computer to run smoothly.
Absolutely. All right, so let's get started. I guess the most basic question is, what exactly is function level reset?
Yeah, break it down for us.
Okay, so FLR, it's a mechanism that's built into the PCI Express standard,
Yeah.
and it lets you reset a single function within a PCI device. Now, when we talk about a function, we're talking about either a physical function, which is like the main hardware capabilities of the device itself, or a virtual function, which is kind of a lightweight virtualized instance of that physical function. And that becomes really important when we talk about things like SRIOV, single root I/O virtualization. But the key takeaway here is that FLR is incredibly targeted. It resets just that one specific function without affecting any other functions on the same physical piece of hardware or any other devices in your system.
So let me see if I understand this correctly. Imagine you've got a high-end network card, right? And it's got multiple network ports built into it. So essentially, it's like having multiple network cards in one physical device.
Yeah, exactly.
So with FLR, if one of those ports starts acting up, you could theoretically reset just that one port without affecting the other ports or taking the entire network card offline. Is that right?
Exactly. That's a perfect example. It's like having a reset button for each individual part of a device rather than just one big reset button for the whole thing.
Oh, okay. That's pretty cool. So instead of having to like reboot your whole system or even just like power cycle the entire network card, you could just target that one specific function and say, hey, you need to restart yourself.
Right. And that's a huge improvement in terms of minimizing downtime and just keeping things running smoothly. And I think that's one of the big reasons why FLR has become so important But there is one important caveat to keep in mind. FLR is not actually mandatory in the PCIe specification.
Oh, so it's not like every single PCIe device out there is guaranteed to support FLR.
Right, exactly. It's an optional feature. So whether or not a particular device supports FLR really depends on the manufacturer, and sometimes even on the specific model of the device. So you can't just assume that FLR is always going to be available.
Okay, so it's like a bonus feature. It's something that you hope is there, but you can't always count on it.
Yeah, that's a good way to think about it. And it's something to keep in mind as we go deeper into this discussion, because as you'll see, the availability of FLR can really impact how certain devices and technologies work.
Got it. All right. So we've established that FLR is this targeted reset mechanism for individual functions within a PCIe device. But why is this such a big deal? What problems does it help us solve, and why should we care?
Okay, so there are actually quite a few reasons why FLR is so valuable, and I think it's helpful to break it down into a few key areas. So first and foremost, FLR allows software to bring a specific PCIe function back to a known clean state without causing widespread disruption.
Yeah.
So instead of having to reset the entire device or even the entire computer, you can just target that one specific function and say, hey, I need you to start from scratch. And this offers some really substantial benefits, especially in a couple of key areas like virtualization and error recovery.
Okay, so virtualization, I know that's a big one these days, with people running multiple operating systems on a single machine or even like spinning up virtual servers in the cloud. Can you elaborate on how FLR is relevant in that context?
Absolutely. So virtualization, it's all about taking a physical piece of hardware and dividing it up so that multiple virtual machines can share it. They each think they have their own dedicated piece of hardware, but in reality, they're all sharing the same physical resource. And this is where FLR comes in really handy, especially when we're talking about SRIOV, single root I/O virtualization, which is a technology that lets you give a virtual machine direct access to a portion of a physical PCIe device.
So instead of having the hypervisor, the software that's managing all these virtual machines, instead of having it kind of act as a middleman and manage all the communication between the virtual machine and the hardware, you can essentially bypass that and let the virtual machine talk directly to the hardware.
Exactly. It's all about giving those virtual machines more direct and efficient access to the hardware, which can really boost performance for certain workloads. But it also introduces some challenges in terms of how you manage and isolate those virtual machines. And that's where FLR becomes crucial.
Okay, so how does FLR help with that?
So imagine you've got a powerful graphics card, right?
Sure.
And you want to let multiple virtual machines each use a portion of that GPU's power. So with SRIOV, you can carve up that physical GPU into multiple virtual functions, essentially little mini GPUs, and then assign each VF to a different virtual machine.
So each virtual machine gets its own dedicated slice of the graphics card. Nice.
Exactly. But here's the thing. You need to make sure that when one virtual machine is done using its VF, it doesn't leave any residual state behind, any leftover data or configurations that could potentially affect the next virtual machine that uses that VF, and that's where FLR comes in.
Oh, so it's like wiping down the whiteboard after a meeting. You want to make sure that the next team coming in has a clean slate.
Yeah, exactly. FLR essentially resets that VF back to its initial state, ensuring that the next virtual machine that comes along gets a clean and isolated environment. And this is crucial for both security and stability. You don't want one virtual machine's mess to affect another.
That makes perfect sense. So in the context of virtualization, FLR is all about ensuring that each virtual machine gets a fresh start with its assigned hardware and that there's no risk of cross-contamination between different virtual environments.
Precisely. And this becomes even more important when you start thinking about things like GPU pass-through, which is a technique that lets you give a virtual machine exclusive access to a physical GPU. This is often used for things like gaming or high-performance computing, where you need the full power of a dedicated GPU.
Oh, yeah, that makes sense. Like if you're running a high-end game in a virtual machine, you don't want any interference from other virtual machines or from the host operating system itself.
Right. And in the past, certain GPUs, especially some of the earlier AMD models, they didn't have very good FLR support. So if you tried to do GPU pass-through with those cards, you might run into problems.
What kind of problems?
Well, imagine you're running a game in a virtual machine, and then you shut down that virtual machine. Now, if the GPU doesn't have proper FLR support, it might get stuck in a weird state. Like it might still think that it's assigned to that virtual machine, even though the virtual machine is no longer running.
Oh, so it's like the GPU is holding on to that previous configuration, even though it should be letting go.
Exactly. And this can cause all sorts of issues, like the GPU might not be usable by other virtual machines or even by the host operating system itself. And the only way to fix it might be to do a full system reboot.
Wow, so in that case, the lack of FLR support can really limit the flexibility and the usability of that GPU in a virtualized environment.
Right, and this is why FLR has become such a critical feature, especially for GPUs that are intended to be used in virtualized environments.
Right.
NVIDIA, for example, they've been pretty good about implementing robust FLR support in their GPUs, so you're much less likely to run into these kinds of problems.
Okay, that makes sense. So in the world of virtualization, FLR is kind of like the unsung hero. It's working behind the scenes to make sure that everything runs smoothly and that virtual machines are properly isolated from each other. But you mentioned that FLR is also important for error recovery. Can you explain what you mean by that?
Sure, so imagine that a specific function within a PCI device encounters some kind of error. It could be a software bug, a hardware glitch, or even just some kind of unexpected condition. Now in the past, the only way to deal with this might have been to reset the entire device or even the entire computer. But with FLR, you have a more targeted approach.
So instead of hitting the big red button, you can try to just fix that one little thing that's causing the problem.
Right, you can attempt to reset just that specific function and hope that it clears the error and allows the device to resume normal operation. And this can be a huge benefit in terms of minimizing downtime and preventing data loss.
Okay, so give us a concrete example of how this might play out in the real world.
Sure, one common example is a graphics card experiencing a black screen crash. You're using your computer and suddenly the screen goes black, the GPU has stopped responding, and you can't do anything.
Yeah, we've all been there. It's not fun.
Right, so in the past, this almost always meant that you had to do a hard reboot. But now with FLR, the system can attempt to reset just the GPU function and see if that brings the display back.
Oh, so instead of having to reboot the entire computer, you might just be able to reset the graphics card and keep everything else running.
Exactly. And if it works, you've saved yourself a lot of hassle and potentially some lost work. So this is a prime example of how FLR can be used to improve the overall resilience of a system by providing a mechanism for recovering from specific errors in a less invasive way.
That's really cool. And I imagine this applies to other types of devices as well, like network cards or storage controllers.
Absolutely. For example, if a network card is experiencing intermittent connectivity issues on a specific port, the system could try to do an FLR on just that port to see if that clears the problem. Or if a storage controller detects an error in a particular I/O queue, it could attempt an FLR on just that queue to try and recover without affecting other ongoing storage operations.
So FLR is like a first aid kit. You can use it to try and fix a specific problem without having to resort to more drastic measures.
Exactly. And this is one of the reasons why FLR has become so important in the world of high availability systems. Systems that need to be running 24/7. You don't want to have to take the whole system down just because one small component is having a hiccup.
Yeah, that makes a lot of sense. You mentioned earlier that FLR is not just about virtualization and error recovery, but also about dynamic resource management. Can you elaborate on that a bit, even if the sources didn't go into too much detail about this?
Sure. So imagine you've got a complex PCIe device, right? One that's got multiple functions on it. And let's say that you want to reallocate some of the resources that are assigned to one function and give them to another function. Now, traditionally, you might have to power cycle the entire device to make this kind of change. But with FLR, you could potentially do it on the fly.
Oh, interesting. So you're saying you could essentially hot swap resources between different functions within a PCIe device.
Yeah, in theory, that's what FLR enables. You could use FLR to quiesce the function that's giving up the resources, then reconfigure the device, and then bring the other function online with the new resources.
Oh, that's pretty slick. So FLR could potentially pave the way for more dynamic and flexible hardware management in the future.
Exactly. And this is particularly relevant in areas like cloud computing, where you have these massive data centers with lots of shared resources being dynamically allocated and reallocated to different workloads.
So instead of having to physically move cables around or power cycle entire servers, you could potentially just use FLR to reconfigure things on the fly.
Right. And this could lead to significant improvements in efficiency and utilization of resources.
Okay, so we've covered a lot of ground here. We've talked about how FLR is used in virtualization error recovery and potentially even dynamic resource management. But let's get a bit more specific now. Can you walk us through some real-world examples of how FLR is being utilized in different types of PCIe devices? We've talked a lot about GPUs, but what about other components like network cards and storage controllers?
Sure. So network interface cards, or NICs, especially those that support SRIOV for virtualized networking, they heavily rely on FLR for managing their virtual functions. So if a specific VF on an SRIOV-enabled NIC needs to be reset, Maybe because of a configuration error within a virtual machine, the physical function driver, which is running on the NIC itself, can initiate an FLR that's targeted specifically at that VF.
So it's like each of those virtual network interfaces has its own little reset button.
Exactly. And this allows the system to isolate and recover from errors that might occur within a specific virtual machine's networking stack without affecting any of the other virtual machines or the physical network itself.
That makes a lot of sense. Now, you mentioned SRIOV a couple of times now. Can you just give us a quick refresher on what that is and why it's relevant to this discussion?
Sure. SRIOV stands for Single Root I/O Virtualization, and it's a technology that allows a single physical PCIe device to be presented as multiple separate virtual devices to different virtual machines.
So it's like taking a single physical network card and turning it into multiple virtual network cards.
Exactly. And each of those virtual network cards can be assigned to a different virtual machine, giving each VM its own dedicated and isolated network connection.
And this is where FLR comes in to ensure that those virtual network interfaces can be cleanly reset and reinitialized without affecting each other.
Exactly. FLR is a key enabler for SRIOV. It's what allows us to manage and maintain those virtual functions effectively and reliably. And this is not just limited to network cards. It applies to other types of devices as well, like storage controllers and GPUs.
Got it. Now, speaking of storage controllers, let's talk about those for a minute. How does FLR play a role in the world of NVMe drives and other types of storage devices?
Okay, so modern NVMe drives, they're incredibly complex pieces of hardware, and many of them are actually multifunction devices, meaning they can present themselves as multiple separate logical devices to the operating system.
So it's like having multiple hard drives in one physical package.
Right, and each of these logical devices or functions might have its own set of resources, its own I/O queues, its own interrupt vectors, and so on. And sometimes you might need to reconfigure these resources on the fly, maybe because of a firmware update, or maybe because you need to adjust the performance characteristics of the drive.
And I'm guessing this is where FLR comes in.
You got it. So instead of having to power cycle the entire drive, which would be incredibly disruptive to any applications that are using it, the drive can use FLR to reset just the specific function that needs to be reconfigured.
So it's like doing surgery on the drive, just targeting the specific area that needs to be fixed without affecting the rest of the organ.
Exactly. And this allows the drive to update its internal configuration without causing any data loss or service interruptions.
That's pretty impressive. Now, I also remember you mentioning something about FLR being relevant to certain form factors of NICs, like those used in server environments. Can you clarify what you meant by that?
Sure. So sometimes you'll hear the term FLR being used to refer to the physical form factor of a network card, for example, flexible LOM rack or flexible LOM blade. These are essentially modular network interface cards that plug directly into the server's motherboard rather than into a standard PCIe slot.
Oh, okay. So in those cases, FLR is referring to the physical design of the card itself.
Right. But it's important to note that even though the FLR in that context refers to the form factor, the underlying function-level reset capability as a PCIe feature is still critically important for managing the individual network functions within those NICs.
So it's like a double, meaning the term FLR can refer to both the physical form factor of the card and the PCIe feature that we've been talking about.
Exactly. And it's important to keep that distinction in mind because sometimes you might see those terms used interchangeably, which can be a bit confusing.
Yeah, especially if you're not familiar with all the different jargon and acronyms that get thrown around in the world of PCIe.
Right. And this is why it's always good to clarify what people mean when they're using these terms because sometimes the context can make a big difference.
Absolutely. All right, so we've talked a lot about the what and the why of FLR, but now I think it's time to dive into how can you walk us through how function level reset actually works at a technical level? Like how does the system actually differentiate and reset just one function without affecting everything else that's connected via PCIe?
Sure. So FLR, it's typically initiated by software. This could be the device driver for the PCIe device itself, or it could be the hypervisor if we're talking about virtualization.
Yeah.
But the basic idea is that the software sends a special command to the hardware telling it to perform an FLR on a specific function.
So it's like sending a targeted signal to that one specific component saying, hey, you need to reset yourself.
Exactly. And there are a couple of different ways to do this. One common way in Linux is to write to a special file that's located in the sys file system. This file is usually located at sys devices BD freeset, where BDF is the unique identifier for the PCIe function that you want to reset.
Okay, so it's like sending a message through a specific channel that's dedicated to that one function.
Right. And when you write to this file, The kernel essentially translates that into a command that gets sent to the hardware, and this command tells the hardware to perform an FLR on that specific function.
Got it. So that's one way to do it. What are some other methods?
Well, another way is to directly manipulate the hardware registers of the device. There's usually a specific bit in the device's control register called the initiate function level reset bit. And if you set this bit, it triggers an FLR on that function.
Oh, so it's like flipping a switch on the device itself?
Exactly. And you can do this using low-level tools like setSci in Linux, which allows you to directly access and modify the hardware registers of PCIe devices.
Okay, so you've got the high-level method of writing to a CIFS file, and then you've got the low-level method of directly manipulating the hardware registers. And both of these methods ultimately achieve the same goal, which is to tell the hardware to perform an FLR on a specific function.
Right, and the specific method that you use might depend on the operating system, the device driver, and just the overall system architecture, but the end result is the same.
Got it. So once that signal is sent to the hardware, what actually happens next? What's involved in the actual FLR process itself?
Okay, so the FLR process itself, it can vary a bit depending on the specific device and the manufacturer, but generally involves a few key stages. First, there's often a preparation phase where the software might need to do some things to get the function ready for the reset, like making sure that there are no pending transactions or outstanding operations that could be interrupted by the reset.
So it's like making sure that everything is in a safe state before hitting the reset button.
Exactly. You don't want to interrupt something in the middle and potentially corrupt data or cause instability.
Yeah.
So the software needs to make sure that the function is essentially idle or quiescent before proceeding with the reset.
Makes sense. So what happens once the function is ready to be reset?
Then comes the actual PCIe level reset. This is where the PCIe controller essentially cuts off power and communication to that specific function for a brief period of time.
So it's like a temporary power outage for that one specific component.
Yeah, exactly. And during this time, the function's internal state is basically cleared out and it's brought back to a known initial state.
So it's like hitting the reset button on a video game. You know, everything goes back to the beginning.
Right. And then once the reset is complete, the PCIe controller restores power and communication to the function, and the function is essentially reborn. It's like a brand new component.
So at this point, is the function ready to go, or is there more work to be done?
Well, not quite yet. The reset itself just brings the function back to a basic initial state.
Yeah.
It doesn't actually configure the function or set up all the necessary resources like memory addresses, interrupt vectors, and so on.
Oh, right, because all of that stuff was wiped out during the reset.
Exactly. So that's where the software comes back in, right? The device driver is responsible for reinitializing the function after the FLR is complete. And this involves configuring all those resources that we just talked about and making sure that the function is ready to resume normal operation.
So it's like the driver is giving the function a crash course on how to be a functioning member of the system again.
Yeah, that's a good analogy.
Yeah.
The driver is essentially teaching the function how to do his job again after it's been reset.
Okay, so it's a multi-step process. You've got the software initiating the reset, the hardware performing the actual reset, and then the software coming back in to reinitialize the function. And this whole process is orchestrated through a combination of software commands and hardware registers that we talked about earlier.
Exactly. It's a carefully choreographed dance between the software and the hardware.
Now, you mentioned earlier that there are different stages involved in the FLR process, and that certain hardware, like the AMD QDMA subsystem, might have dedicated registers for controlling and monitoring these stages. Can you elaborate on that a bit?
Sure. So for simple devices, the FLR process might be relatively straightforward. But for more complex devices, especially those with multiple functions or those that are using advanced interconnects like QDMA, the process can be a bit more involved.
So it's like the difference between resetting a basic calculator and resetting a supercomputer.
Yeah, that's a good analogy. So, for example, with QDMA, there might be a pre-FLR stage where the hardware starts preparing for the reset by resetting internal context and flushing out any pending operations. And then there's the actual PCIe level reset, which we just talked about. And then there might be a post-FLR stage where the hardware performs some final cleanup and verification steps.
And all of this is controlled and monitored through dedicated registers on the device itself.
Exactly. So the software can interact with these registers to initiate and monitor the different stages of the FLR process. And this allows for more fine-grained control over the reset operation.
Okay, so we've talked about how the hardware handles FLR, but let's shift gears now and talk about the software side of things. You mentioned that device drivers play a key role in supporting FLR. Can you explain what their responsibilities are in this whole process?
Sure. So device drivers, they're the software components that are responsible for communicating with and controlling specific hardware devices. And in the context of FLR, they have several important responsibilities.
Okay, like what?
Well, first and foremost, the driver needs to be aware of whether or not the device actually supports FLR. And this information is usually obtained from the device's capabilities registers, which are special registers that describe the device's features and functionality.
So it's like the driver is checking the device's resume to see if FLR is listed as a skill.
Exactly. And if the device doesn't support FLR, then the driver knows that it can't use FLR to reset the device.
Okay, so that's the first thing the driver needs to check. What else is on its to-do list?
Well, if the device does support FLR, then the driver needs to know how to initiate an FLR. And this might involve writing to a sys file, manipulating hardware registers, or using some other mechanism that we discussed earlier.
So the driver needs to be fluent in the language of FLR.
Exactly. It needs to know how to communicate with the hardware and tell it to perform an FLR.
Got it. What else?
And then once the FLR is complete, the driver is responsible for reinitializing the function. As we discussed earlier, this involves setting up all the necessary resources, configuring the device, and making sure that it's ready to resume normal operation.
So the driver is kind of like the coach? It's training the function back into shape after it's been reset.
Right. And the driver might also need to handle any errors or exceptions that might occur during the FLR process, like if the device gets stuck in a reset state or if it doesn't respond properly to the reset command.
So the driver is like the first responder. It's the one that gets called in when things go wrong.
Exactly. And in some cases, the driver might even be the one that decides to initiate an FLR if it detects that the device is behaving erratically or if it's encountering errors.
So the driver is kind of like the brain of the operation. It's the one that's making the decisions about when and how to use FLR.
Right, and this is why it's so important to have well-written and well-tested device drivers, because they play such a crucial role in ensuring the stability and reliability of the system.
Absolutely. Now, we've talked about the role of the drivers, but what about the operating systems themselves? How do they support FLR?
So different operating systems have different ways of exposing FLR capabilities to software, but generally they provide some kind of interface, or API, that allows drivers to interact with the underlying hardware and trigger an FLR when necessary.
Okay, so it's like the operating system is providing the tools and the infrastructure for the drivers to work with.
Exactly. So for example, in Linux, there's the sys file system that we talked about earlier, which provides a standardized way for drivers to trigger an FLR by writing to a specific file.
And in Windows?
In Windows, there's the Device Reset Interface Standard, which is a set of APIs that allows drivers to request different types of resets, including FLR.
Okay, so both major operating systems have mechanisms for supporting FLR, but they might use different approaches or different APIs.
Right, and this is something that driver developers need to be aware of because they might need to write different code for different operating systems in order to support FLR properly.
That makes sense. It's like speaking different dialects of the same language.
Exactly. And then there are other operating systems like QNX, which is a real-time operating system that's often used in embedded systems, and it also has its own API for supporting FLR.
So the takeaway here is that FLR is a widely supported feature across different operating systems, but the specifics of how it's implemented might vary depending on the platform.
Right, and this is why it's important for driver developers to have a good understanding of the different operating system environments and how they handle FLR.
All right, so we've covered a lot of ground here. We've talked about what FLR is, why it's important, how it works at both the hardware and software level, and how it's supported by different operating systems. But before we wrap up, I think it's important to address one final question, and that is, how does FLR relate to other types of resets that we might encounter in the PCIe world? Things like fundamental reset and hot reset.
Yeah, that's a great question. And it's important to understand the distinctions between these different types of resets because they have different scopes, different trigger mechanisms, and different implications for the system.
Okay, so let's start with fundamental reset. What exactly is that, and how does it differ from FLR?
So fundamental reset, it's kind of like the big hammer. It's a system-level reset that affects the entire PCIe device, not just a single function.
So it's like rebooting the entire device back to its factory settings.
Exactly. It wipes out everything and brings the device back to a completely clean state.
And this can be triggered by either hardware or software, right?
Right. So, for example, when you first power on your computer, that usually triggers a fundamental reset on all the PCIe devices in the system. And then there's also the concept of a warm reset, which is a hardware-initiated reset that can occur while the system's running.
So, for example, if you press the reset button on your computer, that might trigger a warm reset on some of the PCIe devices.
Exactly. And the key difference between fundamental reset and FLR is that fundamental reset is much more disruptive. It affects the entire device, whereas FLR is targeted at a single function.
Right. So if you do a fundamental reset on a graphics card, for example, it's going to reset all the functions on that card, including the
Right.
display output, the memory controller, the video decoder, and so on.
Exactly. Whereas if you do an FLR on just the display output function, it's only going to affect that one function, and the rest of the graphics card will continue to operate normally.
Okay, so fundamental reset is like using a shotgun, and FLR is like using a scalpel.
Yeah, that's a good analogy. And another key difference is that fundamental reset is mandatory in the PCIe specification, whereas
Yeah.
FLR is optional. So every PCIe device has to support fundamental reset, but not every device supports FLR.
Okay, so that's fundamental reset. What about hot reset? How does that fit into the picture?
So hot reset, it's kind of in between fundamental reset and FLR in terms of scope.
Hmm.
It's not as broad as fundamental reset, but it's not as targeted as FLR.
Okay, so what exactly does it reset?
So hot reset, it targets the PCIe link, which is the physical connection between two PCIe devices.
So for example, the link between the motherboard and a graphics card, or the link between a PCIe switch and a network card.
Exactly. And when you do a hot reset on a link, it resets the communication protocol between the two devices that are connected by that link.
So it's like resetting the communication channel between the two devices.
Right. And this can be useful for resolving certain types of errors that might occur on the link itself, like if there's a problem with the signaling or the data transfer.
Okay, so it's like a way of clearing out any glitches or hiccups that might be happening on the communication pathway.
Exactly. And hot reset can be triggered in a few different ways.
Mhm.
It can be initiated by the hardware itself. It can be triggered by software, or it can even be done manually by physically disconnecting and reconnecting the PCIe devices.
So there's some flexibility in how hot reset is performed.
Right. And the key difference between hot reset and FLR is that hot reset affects the entire link, whereas FLR affects only a single function on a single device.
So if you do a hot reset on the link between the motherboard and a graphics card, it's going to affect all the functions on that graphics card.
Right. Whereas if you do an FLR on just the display output function, it's only going to affect that one function.
Okay, so to summarize, we've got three main types of resets in the PCIe World Fundamental Reset, which resets the entire device, hot reset, which resets the link between two devices, and FLR, which resets a single function on a single device.
Exactly. And each of these resets has its own specific purpose, its own trigger mechanisms, and its own implications for the system.
And it sounds like FLR is the most precise and targeted of the three.
Right. FLR is the surgical tool that allows us to address problems at a very granular level without disrupting the rest of the system.
And this is becoming increasingly important as our systems become more complex and as we rely more and more on technologies like virtualization.
Exactly. FLR is a key enabler for modern computing. It allows us to build more robust, more resilient, and more flexible systems.
Now, before we wrap up this deep dive, are there any other important considerations or potential challenges related to FLR that we should be aware of?
Yeah, there are a few things to keep in mind. First, as we've already discussed, hardware support is essential. Not every PCIe device supports FLR, so you need to check the device's specifications or capabilities registers to make sure that it's available.
Right. It's like checking the menu before you order,
Yeah.
to make sure they actually have what you want.
Exactly. And then even if the device supports FLR, there's still the issue of driver support. The device driver needs to be written correctly in order to utilize FLR effectively. So if you have a poorly written driver, you might run into problems even if the hardware itself supports FLR.
So it's like having a car with a powerful engine but a lousy transmission,